Hello and welcome. This video gives you some information about the TeachHist package which is available on CRAN. The TeachHist package is a package that is specialized in creating histograms for learning and for teaching. Here we will focus more on the instructor side of the TeachHist package, but I think students can get a good idea how to use the TeachHist package from this video also. What is the presentation goal? The presentation goal is to introduce teaching strategies that can be used together with the TeachHist package. It is not so much to show how you can use the TeachHist package. The TeachHist package is very straightforward and you can use the help system to find out how to use it. Just type TeachHist and run the code. And then a browser opens and you will find the 5 different functions of the TeachHist package. What do we expect from teaching tools in general? Well, the requirement is they have to be visual because we want to use them in the classroom on a big screen. They have to be easy to use on the fly by the instructor, because there's nothing worse for an instructor than to use R or other software in the classroom and you fumble with the code, you make mistakes and everything looks messed up. The code also should be easily to understand by students because they need to know what is going on step by step. How does the TeachHist package accomplish that? The TeachHist package is built on top of ggplot, and since ggplot is visually very appealing, the graphs from the TeachHist package are also. The TeachHist package is way easier to use than ggplot. The reason is that it focuses only on histograms. We have 3 different types of histograms, and for each of these types we will present a short teaching strategy. There are first regular histograms. We have 3 of them: the counts, relative frequency, and the density histogram. Then we have a tool to visualize confidence intervals, and we have a tool to visualize hypothesis tests. Let's go to the code. I usually start with collecting data from my students, for example, about their height. I have that done already. The data are in the data frame data my students. The column where the data are stored is height. Then I use TeachHist counts, the plot argument, to load the data. And here exceptionally, I switch off the second axis. You will see the second axis a little bit later, but for now I switch it off. Execute my code, and here we are. My students know already that the mean is 69.3 of their sample, standard deviation is 4. And here in the histogram, they can see the distribution, how many students fall within each bin. What TeachHist does is it makes sure that the mean is always in the middle of the histogram. That's very important for teaching purposes. Also, the bin width for each bin is by default 1 standard deviation. You can change it, but by default it is 1 standard deviation. So there is another way to generate data. Instead of using data that you already have, you can actually simulate data, and TeachHist will automatically simulate 1000 records. You can change that if you like, but the default is 1000 records. You provide the mean, which was 69.3 in our case. You provide the standard deviation, 4. And in this case, we switch the z-axis, the second axis, on. And because it's on by default, we don't even need this command here. I execute the code. And here's our histogram. Every time I run the code, because these are simulated data, the data will change slightly. That can be useful sometimes, but in most cases we don't want that, so we initialize our random number generator with seed value 1, 2, 3, 4, 5, 6. You can use whatever you like. It's just important you use it again when you want to get the same data. I also provide a font size for the x-axis. I choose 15. And for the labels, I choose 5. This is useful if you demonstrate histograms on a bigger screen so that students can see it from further away. Here's what we get. And this is a perfect occasion to introduce z-values. Because what you can see here is the mean, and obviously 0, where 0 standard deviations from the mean. Students can clearly see that here we are 1 standard deviation below the mean, 2 standard deviations below the mean, here 3 standard deviations above the mean. You can also verify the values using the z-table. We don't do that here. We go to the next slide, and this next slide has the same diagram again. And what I will tell my students is, knowing that 320 students fall in this bin here, or 362 fell in this bin here, is not so useful. What would be more useful is if we have the percentage values. And the only thing what you have to do is you have to change the command from counts to relative frequency. Do this here. Let's not forget to delete the parentheses. And now my students can see how the diagram changes, and what they can see, it doesn't really change too much. The only thing that changes is now the height of the bars are the percentage values rather than the absolute values. Here is the same code again. And we can use it to show the rule of thumb of normal distribution. But it would be nice if we could mark the z-values, because then our students can easier see it. So I will mark the z-values for plus minus 2 standard deviations. And what you can do is you can draw vertical lines into the diagram with the v-line command, and you can draw up to 2. And we set the first one to 61. And we set the second one to 77. Now I execute my code and I get the same picture, but with these vertical lines. Now the talking and the demonstrations for the students become way more easier. It's easy to see what is 1 standard deviation, which is here, and students would see that 68% of the values fall within plus minus 1 standard deviation. 2 standard deviations, I have marked them here with the 2 lines, and students will see that close to 95%, precisely it's 96% here, fall within 1 and 2 standard deviations. This is of course because we have chosen a sample of 1000. You could change the seed value, generate a new sample to show them that each sample is similar than the other, but not exactly the same. We don't do this here. What we do instead is we want to show how we go from relative frequency to density. This is usually something where students really struggle with. We will mark a specific bar here, change the v-lines from 69 to 73. And this is the bar we're talking about. And if we talk about this specific bar, we can say, okay, what are densities? Densities are simply the relative frequencies divided by the bin width. The bin width is 4 here. So 0.36 divided by 4 gives us 0.09. And then the height is not relative frequencies anymore, it is densities. It is important to point out to students that densities themselves most times don't get interpreted, but just stay with it and we will show them later on what the advantage is. So we change this here to densities. By default, density values are not printed. So we change that here, print densities to true. And I execute the code and I remind the students again, 0.36 is supposed to change to 0.36 divided by 4, so to 0.009. I click and students can see what the density is. Well, as we told the students already, we usually don't print the densities because they're difficult to interpret. What is more interesting, that after we created a density diagram, our probabilities are now inside the bar, showing that the area of the bar, not the height anymore, but the area of the bar is equal to the relative frequency, to the percentage of occurring. And with this diagram, we can easily prove it because the area is width, which is 4, which is the bin width, times the height. The height is relative frequency divided by bin width times bin width. Bin width cancels out. And for the area, we are left over with the relative frequency with a percentage of occurring. At that stage, you can change the bin width maybe to 0.5. And what I do, I have an exercise for my students where they have to create, based on this diagram here, their own z-table. That's a little time consuming, but I think it gives students a good idea where the z-table actually comes from in regards of how to interpret it. The next teaching strategy goes with confidence intervals. Confidence intervals requires the sample mean, 69.3 here. The standard error, and I decided not to calculate the standard error inside the tool from the standard deviation. Students have to calculate the standard error by themselves. So standard deviation by the square root of n. Our sample had 34 students. If the standard deviation is estimated, we work with the t-distribution. So you would set is SD estimated to true. Then we have to provide the degree of freedom, which is 33 here. And I changed the axis font size to 12. If you don't want to use the t-distribution, you just delete this part here. That's all what you have to do. We don't want to do it. We want to use the t-distribution because our standard deviation was estimated. And students can see here the confidence interval. So the mean with 95% confidence, and you can change that, falls within these two borders. What you also can nicely show that the confidence interval, which now roughly goes from -2 to 2, changes and gets wider if we have less data. So if our data would be based only on 9 students, then we would have 4 divided by 3 as our standard error, and our degree of freedom would be 8. Then students can focus on the confidence interval. You press run and they can see it gets wider. So the confidence interval highly depends on the number of records. We know that, but it's easy to demonstrate here for students. The last teaching strategy and the last tool I like to show you here are hypothesis tests. What do you have to provide for a hypothesis test? You have to provide the null hypothesis. So let's assume we found on the internet that it is believed that all students' average height in the US is 69 inches. You provide the standard error from your sample. you provide the sample mean, 69.3, and the test type. We do both tails here, but you can also use left tail or right tail. Standard deviation again is estimated, degree of freedom 33. And this time, just to get a nicer looking histogram, we changed the bin width to 0.5. If I execute this here, students can see the green area, which is the fail to reject area, so we cannot fail the hypothesis, and students can clearly see why, because this blue line, our sample mean, is not far enough away from the mean. If it was further away, it would be somewhere here. We can also run a right tail test. Our hypothesis now would be that the true height is greater than 69, because remember, or we should remind our students that we got 69.3. Is that enough to reject the hypothesis? We change the test type here from, and remember, make it singular here, from both tails to right tail. And what students can clearly see here is that they cannot reject, and that is because our sample mean is not far enough from 69 to reject. If it would be further away, they could reject. What I also like to do in these cases, I run a left tail test, which doesn't make a lot of sense, but the diagram will perfectly show why it does not make a lot of sense. Change that to left tail, run the code again. And now, can we reject the hypothesis that our population mean is smaller than 69? And what students can see here is we would need it here in this area, but it is actually bigger. Our sample mean is bigger than our hypothesis. Therefore, even if it was further away, it would not help us. Therefore, students can clearly see that it makes no sense to run such a hypothesis test. They could see already if 69.3 is greater than 69 and their hypothesis is that the sample mean is smaller than 69, they can draw that conclusion right away, even without further steps. That's it. I hope you got some ideas, some teaching ideas. Thank you for watching the video. And if you have any questions, please drop me an email at clang@cpp.edu. If you have questions about how to use the tool for teaching, if you have questions for improvements, please just drop me an email. Thank you so much and goodbye.